So, what happens when the greatest mind in physics, the guy who literally redefined reality, takes a look at the next big theory and says, wait a minute, I think you're all missing something? That's the story we're diving into today, a story about a challenge that still echoes through physics. So, get this it's 1935, and these three guys, Albert Einstein, Boris Podolsky, and Nathan Rosen, they published this paper. But this wasn't just another boring scientific article. No way. This was more like a philosophical detective story. They weren't using fancy lab equipment. Their only tool was pure, razor-sharp logic. And they were on the hunt for a hidden flaw in quantum mechanics. And this was their big question, slapped right there in the title. It sounds kind of academic, right? But what they were really asking was, hey everyone, does this quantum theory of yours actually tell the whole story of the universe, or is it leaving something really important out? All right, so here's how we're going to break down their incredible argument. First, we're going to look at their big question about reality itself. Then we'll get into the rules of the game they set up. After that, we'll dive headfirst into the famous paradox they created. We'll see what they concluded, and finally we'll talk about the mind-bending mystery that's still with us today. Okay, let's start where they did. Because before you can attack a theory, you have to ask a much more basic question. What does it even mean for any theory to be a complete description of the world? Everything they argued hinges on this one idea. For Einstein, Podolsky, and Rosen, let's just call them EPR, a theory had to do more than just predict what would happen in an experiment. A truly complete theory had to have a place for every single element of the real world. If it exists out there, it has to be in the theory, period. Now, if you're going to take a shot at the king, you can't miss. They had to be incredibly precise. So they laid down two fundamental ground rules for their investigation, two conditions for what counts as a fair description of reality. So here's rule number one, their condition for what makes a theory complete. The best way to think about it is like a perfect map. A complete map has to show every single street, every single park, every single building that actually exists. If there's a real landmark out there that's missing from your map, well, your map's incomplete, isn't it? And this right here, this is the absolute heart of their entire argument. It's their definition of what's real. They basically said, look, if you can know something about an object with 100% certainty, like its position or its speed, and, this is the crucial part, you can do it without disturbing that object in any way, then that something has to be a genuine pre-existing part of reality. Okay, so with those rules set in stone, EPR then cooked up this absolutely ingenious thought experiment. The whole point was to use their own definition of reality as a weapon to test if quantum mechanics was actually complete. Here's the setup. Imagine two tiny particles interact, and then they fly apart in opposite directions. Now they could be separated by a few feet or by the entire galaxy. It doesn't matter. The key thing, as you see in step 3, is that they are totally separate now. They're not physically connected, and yet. Quantum mechanics says that when you measure something about particle 1, you instantly know something about particle 2. This is that famous spooky action added distance that so bothered Einstein. It's like the particles are cosmic twins. Even though they're completely separate, they're somehow still linked. Today we call this entanglement. When you measure one, you immediately know something about the other, faster than light could ever travel between them. Spooky is right. And here's where the paradox really sinks its teeth in. As the scientist, you get a choice. If you decide to measure the position of particle 1, then bam, you instantly know the exact position of particle 2. But what if you decide to measure momentum instead? Well then, bam, you instantly know the exact momentum of particle 2. And remember, you never laid a finger on particle 2 itself. This leads us to the critical question. Let's go back to EPR's rule about reality. If you can predict it without disturbing it, it must be real. Well, here we can predict either the position or the momentum of particle 2 just by making a choice far away. So if you follow their logic, it seems that particle 2 must have had both a definite position and a definite momentum all along. So you can probably see where this is all headed. They've laid the trap perfectly. Based on their own rules and their thought experiment, EPR are now ready to deliver the final verdict on quantum mechanics. And here's the final showdown. On one side, you have EPR's logic, which says particle 2 absolutely must have both a real position and a real momentum at the same time. But on the other side, you have a core principle of quantum mechanics, the famous Heisenberg uncertainty principle, which says that is completely impossible. You can't know both precisely. For EPR, the only possible conclusion was that quantum mechanics wasn't telling the whole story. And there it is, the killer line from their paper. They're not just suggesting it, they're saying they are forced to conclude it, that the description of reality given by quantum mechanics is incomplete. I mean, that's a direct challenge. They're arguing that the theory's claim to be a full picture of the universe is just plain wrong.
Now, that paper didn't end the conversation. Oh, not even close. In fact, it was just the beginning. It blew the doors open on a whole bunch of profound questions about the universe that we are still wrestling with today.
Now, let's be crystal clear about something. In the decades since 1935, countless real-world experiments have shown that the spooky predictions of quantum mechanics are, in fact, correct. The universe really is this strange. But that doesn't make the EPR paper a failure, not at all. Its genius was that it forced physicists to stop just doing the math and start asking what all this weirdness actually means. You know, in their final lines, the authors actually admitted they didn't have all the answers, but they shared their hope. They believed that underneath all the quantum fuzziness, a deeper, more complete theory could exist. A theory with hidden variables, kind of like secret instructions that tell particles how to behave from the start, bringing back the kind of common-sense reality they felt was missing. And so, that leaves us with the big question that's still at the heart of the EPR paradox. Is the universe fundamentally fuzzy and uncertain, only snapping into sharp focus when we measure it? Or is there a deeper, hidden layer of reality that we just haven't discovered yet? This question is no longer just philosophy. It's now at the very core of things like quantum computing and teleportation. The debate that EPR started is still raging, and the stakes have never been higher.